Okay, I'm going to work free response question number 6 from the 2004 AP Calculus AB exam. It's actually a combination of a differential equation and a slope field. And so it says consider the differential equation dy dx, the derivative, equals x squared times y minus 1. Part A says, on the axis provided, sketch a slope field for the given differential equation at the 12 points indicated. And it tells us to use the axis in the pink test booklet, but we don't have one of those, so we're just going to do it on this piece of paper. And so whenever you're trying to provide or sketch a slope field, all you want to do is draw little lines, at each point that give you some indication of what the slope would be at that particular point. And so I'm going to start at 0, 0. And so if I start with this point right here, 0, 0, and I plug those two numbers in, notice that I'll put a 0 in for my x value and a 0 in for my y value, just because I'm using that ordered pair right there. Well, when this x value is 0, and I multiply it by this other stuff in the back, it doesn't really matter what this stuff is anymore, because if this front number is 0 and I'm going to multiply by it, then I'm automatically going to get out a 0. So what I know is that at 0, 0, I'm going to have a horizontal line, right? So I'm just going to draw a horizontal line there. And then the same type of logic will continue if I go to the point 0, 1. Because at 0, 1, I'm still going to plug a 0 in for my x value, and then what's back here no longer matters anymore. I'm going to have a horizontal line. The same thing happens when I go to 0, 2, because that x value is still 0. I'm going to get a horizontal line. And then also when I go to 0, 3. So you can see everywhere that my x value was 0, I'm going to get a 0 out for this differential equation right there, so I just need horizontal lines. Now, when you look at this second part and you see that it's y minus 1, what that means is that if I plug a 1 in for my y value, what's inside parentheses will then be 0. So that means that everywhere my y value is 1, I also have a horizontal line. So my y value is 1, over here at negative 1, 1, so horizontal line. And then at 1, 1, so I have another horizontal line there as well. Okay, and that takes care of some of the ones that are a little bit easier. Okay, the other ones we're just going to have to work with. Okay, so I'm going to go right here to the point 1, 0. So that would be the point 1, 0. So 0 minus 1. Okay. So 1 for my x, 0 for my y, and that gives me 1 times negative 1, which is negative 1. So at that point, I need a slope of negative 1. So a slope of negative 1 is going to look something like that. And I'm just aiming for this point right here, because if it was a slope of negative 1, it would go left 1 and up 1 would be something that it could do. So I'm just kind of aiming at that point to get my line fairly close to having a slope of right at negative 1. Okay, my other point is over here. It's negative 1, 0, so a negative 1 for my x value and a 0 for my y value. Gives me 1, because negative 1 squared is 1, times negative 1. So that one's also negative 1. So I'm going to need a slope of negative 1 again. And then I'm going to move to the point 1, 2. So if I go to 1, 2, it'll be 1 squared times 2 minus 1. Well, that's going to be 1 times 1, which is positive 1. So now I have a slope of positive 1 there. If I go to the point 1, 3, then I'm plugging in a 1 for my x, so that's 1 squared, and 3 minus 1 is 1 times 2. So I'll need a slope of positive 2. So that one's going to be significantly steeper. Let me come over now to the point negative 1, 2. So negative 1 squared times 2 minus 1 will be 1 times 1. So it's going to have a slope of positive 1. And then the last one that I actually need to draw out is at negative 1, positive 3. So negative 1 squared and then positive 3 minus 1. So that's positive 1 times positive 2, which is 2. So this one has a slope of 2. So it's significantly steeper than the others. Okay, and that's a rough sketch, but it's a pretty decent estimate of what that slope field would look like. Okay, so once we have the slope field drawn, we'll move to part B. It says, while the slope field in part A is drawn at only 12 points, there is 12 points. It's defined at every point in the xy plane. Describe all points in the xy plane for which the slopes are positive. Okay, so we're looking for where the slopes are going to be positive, which means that we need x squared times y minus 1 to be, and then a way that we could say this would be that this stuff is greater than 0, right? Because this is the derivative, you know. This tells us about slopes. It's a derivative, and what we want is for the slope to be positive. Therefore, we want the derivative to be positive. And so we can just set it up where we have that function right there being greater than 0, and therefore our derivative being positive. Okay? So now I'm just going to manipulate this equation a little bit. And when I manipulate the equation, there will be some things that you can kind of see that are going to happen whenever we do this. Okay? So let me just move some stuff around, and we can talk about what's going to happen here. If we want this stuff to be greater than 0, then what we need is for either both of these numbers right here to be positive, or for both of the numbers to be negative, okay? Because if we multiply a positive times a positive, we'll get something greater than 0. And if we multiplied a negative times a negative, we would get something that would be greater than 0. So those are the two options that we need to think about. So let me just talk about it like this. We need to think about where x squared is greater than 0 and y minus 1 is greater than 0. Or we need to think about where x squared is less than 0 and y minus 1 is less than 0. Okay, so those are our two options. Now, when you start looking at this, the top one makes sense. X squared will be greater than 0 when, so this would be when x is greater than 0. Right, that would be pretty easy. X squared will be greater than 0 when x is greater than 0 and when x is less than 0. Okay, both of those will work for x squared. And then y minus 1 will be greater than 0. You know, if we just did some algebra here and add 1 to both sides, that will happen when y is greater than 1. Okay, so this is an option when we can have something positive. When x is greater than 0, and let me use an or statement here, right? Because it can be either one. It can be greater than 0, or x is less than 0. Okay, and then our y value greater than 1. Remember, what this is going to make happen is this is going to make us have a positive number for the x squared right here, and a positive number for the y minus 1. That's how we set it up. Positive number for x squared, positive number for y minus 1. Okay? And so a positive times a positive would give us a positive, and therefore a number that's greater than 0. Or our second option was that if both numbers were negative, because if both numbers are negative, then a negative times a negative would make a positive. But the problem with this is this right here. It's impossible to square a number and get out a negative. So x squared being less than 0 absolutely won't work. So this second option right here is not a possibility. So our only time when these two, when this function right here is going to have a positive slope or a positive number for the derivative is when our x value is greater than 0 or less than 0. Now it's much easier to say that it's just when x is not equal to 0, right? Because it can be greater than 0 or it can be less than 0. It just can't be 0. So when x is not 0, and our other thing was that y has to be greater than 1. Okay, so when x is not 0 and y is greater than 1, this differential equation will be positive, right? Okay, now part C says find the particular solution y equals f of x to the given differential equation with the initial condition f of 0 is equal to 3. Okay, so there's part C up here. So we're trying to find the solution for this thing. We're trying to get back to, if you'll notice with me, the original equation. Okay, we want y equals something. So I'm going to take this function. It says dy dx is equal to x squared times y minus 1. And I'm going to use separation of variables here, right? So using separation of variables, I'm going to multiply by dx on both sides, and those will cancel, and so dy is equal to x squared times y minus 1 dx. And then I need to get my y's together and my x's together. So I'm going to divide by y minus 1 on both sides, and this will cancel. So dy times 1 over y minus 1. I'm just going to turn this y minus 1's on bottom, so I'm just going to make it this fraction right here. 1 over y minus 1 times dy is equal to x squared dx. And now I just need to take the antiderivative of each side. When I take the antiderivative of this side over here, I'm going to need to use a natural log. And there's really no need for a u substitution, since if I took the derivative of this bottom piece, it would just be 1. So this is just going to be the natural log of y minus 1 is equal to, and then on the other side, the antiderivative of x squared is going to be x cubed times 1/3, right? Add 1 to the power, that gives us the 3, and then we need to divide by that, and dividing by 3 is the same thing as multiplying by 1/3, and then we need our constant of integration, okay? Now that we have the equation, I'm going to go ahead and solve for y. So that means that I would need to raise e to each side so that this e and natural log would cancel. So y minus 1 is equal to e to the 1/3 x cubed plus c. And this can be broken into e to the 1/3 x cubed times e to the c. Okay? And remember, once again, I'm just using a property of exponents here. You know, if you think about it like x squared times x cubed, you know that the answer is x to the 5th. Well, the way you're getting that is x to the 2 plus 3. You're just adding the exponents, right? But in this case, instead of moving from x squared times x to the 3rd to the 2 plus 3, I'm actually going backwards from the 2 plus 3 to the x squared times the x cubed. So what that means is that I can get from here to this right here. Okay, so once I get there, what I'm going to do is I'm going to look at this, and if it's e to the c, you know, anything to a constant is a constant. So this would just be a constant times e to the 1/3 x cubed. And then I want to use my initial condition. So I'm going to plug in a 0 for x and a 3 for y. And so y is 3 minus 1 is equal to c times e to the 1/3 times 0 cubed. So 3 minus 1 makes 2. C times all of this stuff up top is just going to turn into 0. And e to the 0 is just 1. So this is c times 1, which means that c is 2. Now I'm going to take that value for c and plug it in. And so y minus 1 is equal to 2 plugged in for c, e to the 1/3 x cubed. And then to get y completely by itself, I'm just going to add the 1 to each side. So y is equal to 2e to the 1/3 x cubed plus 1. And so there is the original function that they were asking us for.